is Winnie Chen, and I'm an AZOTEQ Product Manager at SELTECH. Today, it is so nice, so many of you joining our SELTECH Sensor Converge virtual event. I think it's time to start our webinar. So what is the plan today, Julio?
Yes, hi Winnie. Hi everyone. Today we will have our partners and friends from AZOTEQ. Our latest range of chipset has capacitive, inductive and Hall effect sensing on a single IC, allowing you to incorporate more functions with less chips. By presenting some current solutions, we aim to inspire you to identify unique user interface for headphones, earbuds and wearables. We love making your wildest idea a reality. We will leave now Paris to join the wonderful city of Cape Town, where AZOTEQ is based. So take a nice cup of coffee, some water, and enjoy this webinar and stay safe.
Good afternoon, everyone, and good morning to my friends on the West Coast. Can you guys hear me okay? Okay. I'm assuming that you are hearing me okay right now. Okay. My name is Abhijit Patil. I'm product manager with AZOTEQ. Today we are going to learn about AZOTEQ solutions in wearable and hearable marketplace and how our multi-sensing solutions can make the product even cooler. So let's get into it quickly. Right. Right. We've been doing capacitive sensing solutions over 2 decades, and lately, over last 5 or 6 years, we have taken over larger share of the wearable and shareable user interface sensors from the market. So today, we are going to learn about AZOTEQ's offerings in wearable and hearable market. The presentations from today is divided into 4 different sections. The first section, we're going to talk about AZOTEQ capacitive sensing solutions in the same market. During the second section, we will talk about inductive sensing solutions and how different form factors of inductive sensing is applied to this market. The third section will include Hall effect sensors, Hall encoders, and towards the last section, we'll learn about our newer chips offering these solutions and how you can combine 4 different sensing technologies onto a single chip solutions. So let's get into it. Let's look at the simplest form of capacitive sensing solution, touch buttons. You may ask why touch buttons are the simplest thing. A lot of people out there, that's true. But we have one of the highest signal to noise ratio in the market. We have sub 2 microamp power consumption on our single channel devices. And these things are really important when you are going to design something for a small form factor such as earbuds. Since the space is an issue, the signal to noise ratio is really important, and power is always important in consumer electronics. To go with it, over the years, we had a lot of successes and failures, and from our successes and failures, we have learned to add a lot of niche algorithms to our touch sensing technology. All these things make a touch designer's job or electronics designer job much easier, and that reflects into our product. That's why our touch button solutions are very sophisticated, robust compared to anyone else in the market. A simple touch button solution on a wearable is tap, which can be used for play, pause, or tap and hold. We also offer slider solutions in capacitive sensing. We've been doing sliders for the last 8 to 9 years. We started with 2 or 3 channel sliders. Our sliders can have a really high resolution for finger tracking. They can be used as a swipe switches. They can be used as a flick switches. You can also have slider output over I2C, or you can also have slider output over GPIO. Now, we have devices which can offer only touch buttons. These are small size, very low power consumption, and really inexpensive devices. And we have devices which can only offer slider interfaces, of course, with the proximity wake up to achieve the low power consumption. And we have devices where we can combine touch buttons as well as sliders. Okay, we learned about touch buttons and sliders. Let's look at our next offering. We just talked about touch buttons. A simplest form of touch button implementation is a wake up button. On a wearable device, touchscreen or just a screen is the highest power consuming device or entity. You cannot have that screen on all the time. One of the most neat ways to handle the power consumption is implementing a wake up button. This wake up button can be capacitive or inductive, but since we are talking about capacitive solutions in this section, I'll discuss the capacitive wake up button. Our single channel IC such as IQS211A, IQS231A can be used to design this wake up button. It can be a really small size. We have done this for one of the leading wristband manufacturer in the world. Most of you guys know our success stories there. The power consumption on this device can be as low as 2 microamp or even lower than that. And it's very critical because your capacitive sensor is going to be on all the time. So it's really important that it consumes the least amount of power while being active at about 120 milliseconds of report rate. So wake up button would be a nice interface from AZOTEQ portfolio for wearable solutions. The next you will see is our trackpads. We've been doing trackpads in various form factors for years. We've been providing customized turnkey solutions to our customers. Under that, AZOTEQ works with the customer, understands their requirement, and engineers a trackpad which is with the full satisfaction to customers' requirement. A lot of our tier one customer chooses this platform or this way of working with AZOTEQ because AZOTEQ brings a lot of engineering value to the table. We design these trackpads, we manufacture them, we test them, and we ship a fully functional trackpads to our customers. Now, let's talk about trackpads in the hearable market space. On the Bluetooth headphones, traditionally mechanical buttons are used, but for a user, it's very difficult to locate these buttons. Or let's talk about the recent or younger generation users. They don't really like these mechanical buttons. Instead of that, the nicer user interface is to design a gesture pad on the side of the headphone. This offers a lot of flexibility to the ID design team to put the logo, make the headphone look nice, have a unique body type of feature, and the gesture pad eventually becomes your Bluetooth controller. Basically, a simple tap can be used as a play or pause. At the same time, a swipe forward can be used for skipping track. Swipe backward is going back to the previous track. Swipe up and down can be used for the volume control, and the multi-finger gestures can be implemented to enable Alexa or Google. So a gesture pad in a Bluetooth headphones makes up for a really, really sleek interface. And we have customized solution available, and we also have some standard trackpad solutions or standard gesture pad solutions available out of our portfolio. Now let's expand a little bit on these trackpads and how they can be utilized in different ways. The first picture you are seeing on your slide is a trackpad with buttons. We just talked about how to getting rid of the buttons, but at the same time, there is a small section of customers who still like these mechanical buttons. So AZOTEQ has a technology which can control the metal domes on the trackpad capacitively. What that does is that allows you to implement a trackpad and a mechanical buttons on a same surface. This reduces strain on MCU to have more GPIO or managing the snap domes. At the same time, the routing becomes easier, the connections or the connector pin count becomes easier. So it's a lot more advantageous to do it this way. So AZOTEQ can detect this snap-dome's activation and report it via I2C along with gesture pad or trackpad output. We have done this for various customers. We have this technology available for 7-8 years now, and we know ins and outs of how to implement it. So this is a nice way to deliver a combination of a trackpad and a mechanical button interface to the clients. We talked about over-the-ear headphones, but that's not where the trackpads are restricted to. You can take the trackpad and take them to a really, really smaller size and implement them into earbuds. The feature set still stays the same. You can use that for skipping tracks, going forward, backwards. You can use it for the volume control. You can use tap and hold type of gesture for play and pause, or just enabling Alexa or Google commands. The thing here to notice is we can take our size of the trackpad and reduce it all the way to the 8mm diameter. I want to go ahead and claim that nobody in the market can deliver an 8mm diameter functional trackpad out there, and AZOTEQ has a technology to do that. So earbud trackpads are not out of reach. We have done a slightly larger form factor trackpad for one of the tier 1 customers out there. Many of our partners know the success story, but we are taking this further and reducing the size of the trackpad in the earbud form factor, because let's face it, the earbud sizes are getting reduced day by day. The last in the list here on this slide is the custom trackpads. You are looking at the picture where we have a trackpad along the side wall of the headphone. This is basically just a slider, more of a slider than a trackpad, but the picture shows that our flexibility and customization capability to deliver different types of user interfaces according to customer requirements. Okay. We just learned about our basic capacitive sensing solutions in the wearable and hearable space. Let's talk about inductive sensing solutions. So this is something unique. Some of you know about inductive sensing solutions, some of you don't. This is a really nice opportunity to get familiar with it. We'll start. There are 3 different types of inductive sensing we'll discuss today. The first one will be the force sensing. The second one will be a waterproof switch. And the third one is contactless switch / waterproof switch for the wristbands. The first 2 offerings we will discuss it in hearable market space, and the last one we'll discuss in the wristband form factor. What is force sensing? Force sensing is a simple deflection of the outer housing, a very minimum deflection where you don't feel like you're putting a lot of pressure on it. And this small deflection is picked up by inductive sensor. AZOTEQ can detect this deflection as low as 2 micrometer, one of the most sensitive out there in the market. And this offers a really nice user interface. A simple squeeze on the earbud stem can produce this function. We'll learn about the inductive sensing constructions in the next slide. But just why inductive sensing? Why not capacitive sensing? So there can be an application where the waterproofness is required. Capacitive sensing is a really nice interface, but at times it can have it on limitation depending on application requirement. So if the application requires little more robustness than what capacitive sensing offers, the force sensing is a nicer implementation out there. Force sensing works with hair above pressure than the simple touch. So the user doesn't feel like they're putting a lot of pressure. It's not like a really forcing the body. It's a simple squeeze on a stem, and it's a hair above pressure than a touch sensing, and it can activate a function. And that's a pretty good user interface, pretty neat user interface with a lot of robustness added to it. Since it involves a mechanical deflection, it doesn't get false triggered with water. Let's look at construction of a force sensor onto earbud form factor. On the left hand side of your screen, you are looking at a FPC with the extended metal target on top. So if you look at neatly on the bottom of that FPC PCB coil is designed in, the extended metal is bent over backwards and sitting top of the coil, and it's separated by a sponge. As the user puts the force on the top plastic, the top body deflects, or it changes its position from it changes its original position, which eventually translate that force onto a metal, and the close vicinity of that metal is picked up by coil and reported over I2C or GPIO interface. So basically, you are looking at a simple coil and metal. As the metal comes closer to the coil, the inductance of the coil is changed, and that's reported to the system. The deformation of the sponge is not an issue here if you use a right material from a longevity point of view, since the force placed on the top plastic is such a little that the sponge doesn't really go through a lot of deformation. And the sponge there makes sure that the metal body is always returned to its original position all the time. Now, some of you may say, hey, this looks like a really a big compared to what our customers have requirements. So for smaller sizes or where the area is a constraint, you can use an SMD inductor as an inductive sensor. You can have a pogo pins as your metal activator. Of course, compared to your PCB coil type of design, the SMD inductor and pogo pins are more stricter alignment requirements, but that's not anything which cannot be achieved. You can also use the pogo pins and design the coil in a really small size. We have tested the coils as small as 3 by 3 millimeter. We usually need a single layer coil in our design, but it can also be used a multi-layer coil if the size of the coil can be really small. Now let's further expand on the construction. This slide shows a different way of implementing a force sensor. We just looked at the force sensor into hearable. Let's look at the force sensor into wristband. So it puts a different perspective forward. Here, the PCB is there behind the plastic. The plastic will need to have some sort of a metal insertion. It can be a conductive paint, it can be a copper tape or something similar which works in the production environment. As the user puts pressure on the top outer housing, the housing is deflected and the inductive coil detects the presence of the metal in the close proximity and is reported to the system. This is a simple construction. It works with or without silicon band. It's not a requirement. It's 100% waterproof. And the basic principle is moving the metal target closer to the inductive coil. Okay, so you guys learned about inductive sensing and derivation as force sensing. One of the things I would like to include is in our force sensing measurements are relative measurements. They are not absolute measurements, so we are not going to report, hey, exactly how much pressure is being placed, but we are going to report the pressure is being placed. You can further expand this force sensing depending on the form factor, not applicable to this markets, but you can actually have different steps of force detection onto different levels of force detection as well. So we learned about force sensing in the wearable space. Let's learn about how to design a waterproof switch. So mechanical switches are still popular out there in a lot of applications, solely because of the tactile feedback they provide. Because of that tactile feedback, customers are not willing to go away from the mechanical switches, but it also makes it challenging to design a mechanical switch for a waterproof assembly. The whole mechanical assembly becomes a lot tedious, it gets expensive, and still you cannot 100% deliver a waterproofness. So there's a way you can use an inductive sensor to design a waterproof sensor. The principle is since inductive sensing is a contactless sensor, you don't have to have any outer body physically shorting or in contact with the electronics. So the way principle works is you can have the electronics inside the sealed plastic. On top of it, you can actually implement a metal dome switch. As the metal dome switch falls with the user pressure, the deflection in the metal dome is picked up by the inductive sensing and is reported as a change in inductance. So let's look at that here. We are looking at this picture. Here is your button for user interface. That's your coil inside the plastic, and that's your metal dome. As these three things comes together, you can see there is no physical contact of the coil with the outer assembly. So this way you can have your waterproof button, you can have your tactile feedback out of the metal dome switch, and you can also have your waterproof aspect of the design maintained without having a complex mechanical assembly. The right-hand side picture shows just a different variation. The waterproof switch can also be implemented on the stem of the earbud. Now, we learned about force sensing from inductive sensing. We learned about waterproof switch from inductive sensing. Let's look at the waterproof button from the inductive sensing. This is a similar thing we just looked at as a waterproof switch, but in this particular design, we are looking at the wristband application. There may be a metal dome, or there may not be a metal dome, or there can be some sort of just a silicon type of membrane type of design in between to give a slight tactile feel. This is already tested and popular in the market, so you can use the inductive sensor to design a waterproof switch. The construction stays very similar. The inductive coil is inside the sealed assembly. The top body can be a plastic, or it can be a metal object or metal body. As a user puts little bit force on the button, it deflects from its original position, and the change in the inductance is picked up by our inductive coil. I would like to reemphasize again, one of the things you would be talking, if you're a customer or if you're a channel partner, one of the things is important is minimum deflection needed to activate the inductive switch. It can be as low as 2 micrometers. Okay. So we learned about capacitive sensing in hearable and wearable space. We learned about inductive sensing in hearable and wearable space. Let's look at our third section of this presentation, Hall solutions. So AZOTEQ has a dedicated Hall encoding solutions. Hall encoding solutions, popularly known as Hall rotary solutions, they are very similar to your optical encoders, mechanical encoders, or just your parts out there. But at the same time, they have advantages over all those competing technologies. Hall encoders is a contactless sensing. The basic principle involves is you have Hall plates embedded on the IC, and as a dual pole magnet rotates on top of the IC, there is a phase shift, and this phase shift is used to calculate the accurate position of that rotating magnet. Because we can accurately detect the position of the magnet at every small point, it gives us an advantage over optical encoder, where Hall encoders can report absolute positions compared to optical encoders are only limited to report relative positions. Of course, there is a wear and tear and low resolution issue with the mechanical encoders. Some carbon contact encoders are also relative positioning reporters, and at the same time there is a wear and tear issue, and the parts are very traditional old way of doing encoding. Hall encoders are actually, just so you guys know, Hall encoders are sophisticated technology for rotary encoders. They've been popular in automotive industry for years, but automotive Hall encoding solutions are really expensive. They are over $1 solution. AZOTEQ is bringing Hall encoding to the consumer market at much more less price. Our main customer base is consumer market. We understand the price pressure, and that's why our Hall encoding solutions are in high 30s to low 40 cents type of solutions. So let's look at some of the construction of the Hall encoding solutions and application. The picture on the right-hand side shows you the typical construction of a Hall encoders in a small form factor. So there's a magnetic stem, it's a dual pole. There is a digital crown, a user moves the digital crown, and then AZOTEQ IC is detecting the phase shift because of these poles. We have, on a previous generation of our devices, we had 2 Hall plates. On our existing hardware platforms, we are going to have 4 Hall plates. That means more accuracy on our Hall encoding solution. Presently, we have about 10 bit of resolution. This is one picture we have included in the hearable space for over-the-ear headphones. You guys also know that a lot of headphone makers out there do have a total rotating outside cup that can also be implemented with AZOTEQ Hall encoders. Just don't worry about the form factor. It can be expanded or it can be reduced. The rotating can be big or it can be really small. This picture, we just wanted to emphasize how small we can get so you guys can think of different places where our encoded solutions can be implemented. On the left-hand side, you are looking at the wristband, the crown on the wristband. Let me take that back. It's not a wristband, it's a watch. So yeah, the watch, the crown on a watch is a typical user interface, but digital crown on a watch has been popular lately. It's been implemented by some of the popular watchmakers, not so traditional watchmakers, but they're making watches. And digital crown is definitely can be implemented using AZOTEQ encoder. The important thing to notice here is the size of the coil. Presently we have CSP 16 to CSP 11, really 3 by 3. CSP 16 is 1.68 by 1.68 millimeter size, and CSP 11, I don't remember the size, but it's much smaller than CSP 18. So size of the IC is not a problem. Getting into smaller factor is not a problem. And I would also like to point out that we can combine our Hall sensing solutions with capacitive solutions or inductive solutions. So you can have this crown on that watch implemented with Hall encoder. At the same time, it can be a click switch with inductive switch, or it can be a simple proximity or touch button on the outer of the digital crown. You can also take the Hall encoding technology and implement that onto a earbud form factors as well. So since we have the Hall plates, we can also do a Hall switch. The Hall switches in wearable space are almost, you will find them in every earbuds out there. They are used for a lead detection on the charging case. They are used to detect if the earbud is plugged in the charging case or not. You can use this additional information to turn the Bluetooth on or off, conserve the power, have a more efficient pairing mechanism, and as it's not necessarily a single different solution. Since it's part of our multi-chip solutions, this becomes a really attractive to our customers. You can have our IC placed on in the earbud, or you can have the IC placed onto a charging case. You can also modify the charging case to add neat user interfaces from our capacitive sensing or inductive sensing. And you obviously also just learned about our user interfaces onto earbuds as well. So this completes our 3 sections and the technology. Let's look at the devices. So we have come up with a dedicated wearable touchscreen device where we will have, the device will have 42 nodes. It will do a single finger touchscreen control on your wristbands. At the same time, you will be able to implement a force switch or a tactile switch or waterproof buttons, or just a simple touch button on your wristband. Let's look at the device. The device is IQS7210A. This is dedicatedly developed for wristband applications where you can have a touchscreen control. At the same time, either you can have a waterproof button or you can have a force switch to go with it. The device, like I mentioned, it's a fully trackpad or a touchscreen up to 42 nodes. 42 nodes are more than enough to cover Apple Watch or iWatch type of form factor. So it can fit most of the applications out there. It also comes up with the Hall sensing capabilities. So if you have any charging or docking detection type of applications, you can also take advantage of our Hall sensing technology in there. AZOTEQ has been doing wear detection close to 8 to 10 years now. We have implemented a lot of unique user interfaces in the past to do a wear detect. Every time we learn something new, and every time we introduced a device to the market, it reflected our experience, and sophisticated algorithms made designers' job a lot easier. So now AZOTEQ is coming up with new technology called WearMax. It's a very unique capacitive sensing technology. There is no one out there offers this. The unique thing about this is it has auto drift compensations. It has a mirror sensor which actually takes care of all calibration, and your main sensor doesn't have to be calibrated all the time. We can distinguish if the user is actually wearing the headphone or they're just adjusting the headphone in the ear, or WearMax technology will enable us to detect those differences. These things, the WearMax, like I mentioned, this is very well designed for taking care of different types of environmental drifts, and we have a very unique offering in the market, and this is definitely a one of the biggest advantages we have out in their competition world, where nobody is coming to close offering a wear detect solution as AZOTEQ. On top of that, we have added our WearMax sensing to the portfolio. Now we learned about capacitive sensing solutions, we learned about inductive solutions, we learned about Hall sensing solutions, and we learned about wear detection solution. So the important thing here is we can combine all this sensing technology onto a single chipset. It reduces the power management, it reduces the supply chain management, which is a very crucial thing in 21 and 22. We can combine touch swipe interface. We can either have waterproof touch button or force sensing, or one of these added to the solution. Of course, the docking detection or the Hall sensing is part of our ICs, and we can also add a wear detection. So having the 4 different user interfaces out of a single chip is advantageous in many different aspects: power consumption, the bill of material, the supply chain management, or even the technical support. You don't have to just go and ping 4 different vendors to get things right, because one vendor is providing this solution. Also, keeping in mind the size of the electronics and size of the earbuds is getting smaller day by day. So it makes a lot more sense to have a single chipset handling multi-user interfaces out there. Next slide, I'm going to go over quickly on how you can implement this force sensing. Definitely, this is not the only way to do it. This is just something we wanted to put in a presentation, so it gives you an idea how this 3 or 4 sensing technologies can be implemented together. The Hall sensing is local; it's native to the IC. Since it's out of Hall plates out of the IC, you can see there are 3 capacitive electrodes are implemented on the right-hand side of the screen. They can operate as a simple touch button, or they can operate as a swipe switch or a slide switch. And then the wear detection technology, which is needs to be implemented closer to the ear, just to make sure it's in close contact with the body, and somebody is not just holding the headphone in the hand. You can also implement a force switch or just a waterproof inductive switch on the earbud stem as well. So this is how you will be implementing 4 different sensors on a single chipset. Our FAEs are very used to working with this type of form factors. Like I said at the beginning of the webinar, that we have taken a larger share of the market in the last 5 to 6 years in the wearable and hearable space. Our portfolio or our product successes out there, our partners or the customers who have used our technology speaks for that. We have been part of a lot of tier 1 products out there, products which actually are gold standards out there in the market, and we are continuing to evolve. We are coming up with newer hardware platforms. We have just launched our 7 series devices, which are definitely applicable to this market space. We are set to launch our 3 series of devices, which are going to be a low cost solutions, and then towards end of next year, may not be relevant to this presentation, but we will be launching our precision trackpad. So we are continuing our R&D, trying to come up with new user interfaces. Some of the interfaces you may have learned in past years from AZOTEQ, but we have added new algorithms. We have added little sophistications, and we are set to launch this in year, and next 1 more year we will be coming up with a lot of newer devices as well. So right, definitely we would love to get in touch with you. We would love to hear back from you about different requirements out there in the market and how you will be utilizing AZOTEQ sensing solutions in your design. So Julio, time for questions.